Okay, hello everyone. Welcome to the fifth lecture in Introduction to Stable Homotopy Theory, and finally we will start talking about stable homotopy theory. I'm sure it is a relief for every one of you. It is certainly for me. So, okay, let me quickly remember a bit the characters that will appear today. So we're going to have this space is going to be the infinity category of spaces, and remember, we formally defined it as the coherent nerve of the category of Kan complexes, but the precise definition is not really important for today. And it is going to be for well, the intuition you should have, objects are spaces, maps are continuous maps, homotopies are homotopies, and so on and so forth, as you expect. Sorry, when I say space, I mean space is homotopy equivalent to CW complexes. And importantly, will be also the infinity category of pointed spaces, which, for example, you can define as the coherent nerve of pointed Kan complexes, which are Kan complexes with distinguished points and maps that preserve the distinguished point. There are other ways of defining it, but that's not important. And remember, important thing that we discussed a bit last time, the homotopy category of spaces, which happens when you identify homotopic morphisms, is the same thing as the homotopy category of pointed spaces, well, of pointed CW complexes. That we discussed, we discussed last year, or whenever you have studied algebraic topology. Okay. So important facts that we're going to need. The important fact is well, the important fact is spaces, pointed spaces can be generated under colimits by spheres. When I write Sn, you can, choose whichever model you want for the homotopy type of Sn. They can actually give you an explicit Kan complex model, but that's sort of besides the point. So what does this mean? It means essentially you can think of these as every space has a pointed space has a cell structure. You can think of it, I don't know, every space X can be written as the colimit of its skeleton. Let's see, and skeleton. And for example, you can realize the n+1 skeleton by taking this homotopy push out by attaching a bunch of cells. You might have seen these as taking the wedge of a bunch of disks, but of course, up to homotopy, this makes no difference because a wedge of disks is just contractible. And I'm sort of going to stop to distinguish between homotopy equivalent spaces now, since now we have all the technology that allows us to treat them as interchangeable. Okay. These shouldn't be a surprise for anyone, but do you have questions about this? Okay, if you don't, let me introduce let me first add an definition I should have given last time. A co-fiber sequence that I'm going to write as x prime goes to x double prime is just homotopy. I said I wouldn't use homotopy anymore. A push-out diagram. X prime goes to X double prime, goes to the point. So concretely, this means that we have two maps, F and G. So concretely, we have F, G maps, H, homotopy of GF with the constant map at the point. And which is universal. And if you remember, last semester we saw that these IE, G, and H identify X double prime with the mapping cone of F. Remember. And the mapping cone of F, we will often write the mapping cone of F as cof F or X mod X prime. Because you remember, when F is a cofibration in topological spaces, this is equivalent to X mod X prime. We saw this last semester. Although we won't need it just to motivate the notation. Or sometimes also CF, but I'm going to use it less often. Okay. Questions? No? Okay, so it's time to actually start, finally, with the main definition for today. This is not the most general definition I can give, but it turns out to be equivalent. It's going to be an exercise in the next week exercise sheet that is equivalent to the more general thing you might want to give. But let's work with this for today. So a cohomology theory is a pair E upper star delta, where delta E upper star is a map from the homotopy category of pointed spaces up into graded abelian groups. Let me spell out what this is. Graded abelian groups. And delta from is a natural isomorphism of E star with E star shifted, composed by sigma, where sigma is the suspension. Remember, suspension, we saw it as a functor from pointed spaces to pointed spaces, but of course it induces a functor in the homotopy category, so this makes sense. This might or might not be the definition you've seen before. Oh wait, I didn't tell you the property though. Such that, so we have two properties. For any collection of pointed spaces X alpha, the map, so we have a map from E upper star of the wedge. Remember, the wedge is the coproduct to the product. Is an isomorphism. And a tiny bit of warning. The product on the right-hand side is the product in graded abelian groups. So it means that in every degree you take the product. So it's not if you see an abelian group, a graded abelian group as the sum of its homogeneous parts, this is not literally the product of those. You get, when A is infinite, you get a different thing. So if you prefer, you can put this condition by replacing star with n for every integer n. Okay, that's one condition. That's not particularly interesting. The most interesting one. But let me also notice that when A is empty, this tells you that E star of the point is 0. That's a special case of this condition, but let me spell it out explicitly. Because we're going to need it to state the second one. So for every cofiber sequence, which remember is given by x prime, f, g, x double prime, and a homotopy, h, a null homotopy of gf with a point. The sequence E upper star of x double prime, g upper star of x to E upper star of x prime is exact in the middle. Okay. So these are the two conditions. They shouldn't be a surprise. You should have seen at least one example of this before, and let me actually give you this example. So example, let M be an abelian group. Then X goes to the reduced homology of X with the coefficient of X, equipped with the suspension isomorphism, is a cohomology theory. And you should have seen both properties. And note that I am actually hiding a third property in the definition, which is homotopy invariance, since it is a functor out of the homotopy category. And that's the same thing as it's saying it sends homotopic morphisms to the same morphism. It's more convenient to hide it there in the source category, but in fact, I could have secretly not put this H and ask a functor from the infinity category, since the target is a one category, so it's forced to identify homotopic morphisms anyway. But let me be explicit for now. Okay. Is this definition clear? Okay. Our goal today is going to be no less than to describe all possible cohomology theories. In order to do so, first let us see a bit of the consequences of this definition, what kind of structure you're going to have in this cohomology theory. So first, recall from last semester, you have a cofiber sequence. Then there is a canonically chosen cofiber sequence here. So we can shift things. And actually, let me give you, we saw this last semester, but let me give you a short argument. So we have a homotopy push-out diagram here. We can consider this push-out here with no, sorry, this push out here with whatever this push out is. And if you look at the big diagram, though, it is also a homotopy push out diagram. The big square is also a push out square. So this forces the question mark to just be the suspension of x prime. And then the second square is the square it's the cofiber sequence we wanted. And of course you can iterate this. And we get, for example, x double prime, sigma x, and here you see that what you get here is sigma f, possibly with a minus, depends exactly which conventions you work with, but I'm not going to pay a ton of attention to the signs for now. And then we go. The signs are important in other circumstances, but you can always, choose them coherently, etc. So this sometimes it's called rotating cofiber sequences or exact sequences, but it's a very basic and simple thing. You can actually think it geometrically. If you take x double prime being a mapping cone, and you are you're attaching a cone on this x here, what you get, you can see immediately that it's equivalent to the suspension of x prime by collapsing this cone here, whose inclusion is a cofibration. I think we discussed this last semester. If not, maybe spend some time drawing pictures until you convince yourself that this actually makes sense. So that's x double prime. Oh, so sorry. Let me actually use colors, so maybe it's good. So this is x prime, this is x, this is a cone on x, and this whole thing is x double prime over x. So this is the suspension of x prime is indeed x double prime over x. Of course, this pasting here, it's also a sufficient proof, but maybe familiarizing oneself with the pictures that you can draw is also helpful to keep this concrete. Okay. But okay, what can we do with these rotating fiber sequences? Well, now if E star D is a cohomology theory, we know that you have, for example, En of x prime, x double prime, sorry, goes to En of x goes to En of x prime, and this was G upper star, F upper star. Oh, and I'm doing this. Sorry, I'm doing this wrong. Okay, that's an exact sequence in the middle, but this coming from x prime goes to x double prime, but we also have this thing here, which I'm going to write like this, x, still with G upper star, x and double prime, and then I have this weird that I call the upper star from En of sigma x prime. This is the same, and remember we have our suspension isomorphism with En minus 1 x prime. And you can actually go further, take x double prime goes to sigma x prime goes to sigma x, and here well, let me just write what the result is. You get n minus 1 x prime, and here you get an en minus 1 x. And all these sequences are exact. So pasting all of these together, we get a long exact sequence. En minus 1 x prime goes to en minus 1 x, sorry, en minus 1 x prime, en of x double prime, en of x, en of x prime, en plus 1 of x double prime, etc. So even if our hypothesis gives us only a sequence exact in the middle, we can use the suspension isomorphism to patch them together and get an actual long exact sequence. And let me give names actually. So we have G upper star, F upper star, and I'm going to call them delta upper star. These guys. This was F upper star again. G upper star, G upper star. And these shouldn't be a particular surprise for you. And moreover, a little piece of notation. I'm going to write en of x comma a when a is, well, say a subspace of x. Write them in the other order actually. This is just going to be defined as en of the mapping cone. And we gave it an exercise, I think, twice, that this recovers the classical notion of relative homology in the example that we saw. I'm tempted to give it for the third time, but I think this might be overselling the point. So the long exact sequence, so for the inclusion, so for the cofiber sequence, ax goes to x mod a, the long exact sequence above is the less of a pair. Okay. And it's actually the one for reduced cohomology. You can also define unreduced cohomology by adding a disjoint base point, but I think I'm always going to work with the equivalent of reduced cohomology, at least for today. Okay. Let me pause for 1 second and ask if there are any questions.
Excuse me, maybe a dumb question, but could you quickly recall this suspension isomorphism you were talking about before?
I mean, the suspension isomorphism is part of the data for a general cohomology theory. It's just telling you that the cohomology of a suspension, if you want to.
Okay, thank you, yes.
And it was a theorem that I think you did in algebraic topology 1, that such a thing is there for ordinary cohomology. If you haven't seen it before, the idea is to use the Meyer-Vietoris sequence for so this is the suspension, right? And you can use the Meyer-Vietoris sequence for the upper and lower cone. Maybe thicken a little bit so they become open, I don't know. You can take, for example, this piece and that's not the right color, this this, and this gives you an open cover, and you can write down the Meyer-Vittori sequence for that, and that will give you a suspension isomorphism, if you don't recall these from algebraic topology 1.
And for this, you don't any niceness condition on the map from the base point to your space?
I mean, that's why I defined it as pointed Kan complexes, because yes, you need that to be a cofibration for these to work. What's called a well-pointed space, but since we're basically working with pointed CW complexes here, that's not going to be an issue. And if your pointed space is not nice, you can replace it, for example, by taking the geometricalization of its SING, and we'll give you a weakly homotopy equivalent guy that is that is good enough. Okay. Further questions? Hopefully this definition of cohomology theory is not too astonishing. It's kind of minimalistic in the sense that we are giving the least possible amount of properties that we need to set up the theory. You can deduce all the properties you want from these two. It's a sort of a simplification of the Allenberg-Steenrod axioms, if you've seen the Allenberg-Steenrod axioms before. But if you haven't, we're just going to take these as a definition. You can actually play this game and see, for example, that you get the Meyer-Vittori sequence for an open cover. You can get everything out of this data. Okay? Good. Because our goal is to prove the following result. Well, I'm going to keep it vague for now. We're going to prove a precise result before the end of the lecture, but the goal is for any cohomology theory, E up star delta, there exists a sequence of spaces, of pointed spaces, sorry, xn, such that En, oh, sorry, let me call them Yn. En of x is just, as a set, is pointed homotopy classes of maps. That's the first version that I'm going to tell you of the Brown representability theorem. We're going to be more precise than that. We're going to want more structure on these spaces, but okay. Okay. So the main result here that I'm going to prove today is the following theorem. That's actually what's typically called the Brown representability theorem. Which is sort of representability, sort of an unstable version of the results above. But so let H space pointed greater or equal than 0, side H space star, be the subcategory of connected, by which of course it's the same as path, connected, and etc., because we're working with nice spaces. Connected pointed spaces, sorry, that's also important. Then a functor f from H space greater or equal than 0 up into set is representable, i.e. there exists Y with the property as above, if and only if it has the following two properties. So one, for any collection X alpha of pointed connected spaces, the map F from the wedge to the product is a bijection. Okay. And two, for any push out square, and again, I mean a homotopy push out, the map f of y prime into the pullback. I mean, we might want to ask that it's an isomorphism, but that's actually too much. It's not true for everything. But you want to ask that it's surjective. Okay. Actually, let me put this here so you can see it better. Okay. So that's the statement. These are two properties. The first is fairly, sorry, did someone wanted to ask a question?
Yeah, I wanted to ask a naive question about surjectivity. So does it have to do, the fact that we don't have bijection, does it have to do with the fact that we go into sets?
Yes and no. It has more to do with the fact that a homotopy push out is not a push out in the homotopy category. So for example, imagine that you have a if it's representable, imagine you have a representable by, actually, let me call this Y, let me call it Z. Imagine you have a map from, giving a map from Y prime to Z is not the same thing as, so if F were a representable functor, right, what the left-hand side is the homotopy classes of maps from Y prime to Z, right? And the right-hand side instead is the pairs of maps from Y and X prime to Z such that the composition is homotopic. But you actually know that a map from Y prime to Z is a pair of such maps plus a homotopy. So it's surjective because the fact that these two maps are homotopic means that a homotopy exists, but there might be more than one choice. So the map is not injective. So if you want,
yeah, okay, great, thank you.
The right-hand side is the space. Yeah, I don't know. Maybe I'll spell it out in words in the proof, so I can write it down. But that shows that you cannot ask for bijectivity because homotopy push out has additional data, has also the data of the homotopy, which the right-hand side here ignores.
But the push-out square here is a homotopy push-out.
Yes, yes, yes. I'm not going to repeat it every time, but all limits and colimits here are going to be homotopy limits and homotopy colimits. Well, this one is just a normal pullbacks because it's in sets, and in sets homotopy pullbacks and pullbacks are the same. So you don't have to worry about that. But in general, I'm always going to assume that limits and colimits are homotopy. And I will very rarely be interested in non-homotopy limits and colimits.
Another small question, sorry. So why is the greater or equal than 0 in the symbol for the connected spaces?
Thank you for this question. This is an extremely important fact. It's a remark. I want to spell it out. Both pointedness and connectivity in the hypothesis are necessary. There are counterexamples of functors satisfying 1 and 2 that are not representable if you don't assume. For example, there exists a functor f from the homotopy category of pointed spaces up into set satisfying 1 and 2, but not representable. So that's not an optional part of the argument. Essentially, the point is that pi 0 is not a group. We will see that we're going to use the fact that a map in homotopy groups is injective when if and only if it has trivial kernel. But this is of course not true for pi 0, which is not a group. It can have trivial, the preimage of the base point might be a point, but the map might also not be injective on pi 0. The example is slightly elaborated. I wish I could give it to you. If I can find a simple way of constructing it, it's going to be a worked exercise in the exercise sheet. But it depends on the existence of a group with a certain property. And I'll see if I can give a reasonable construction of this group.
Okay, thanks.
That's very important. Oh, there are also counterexamples without pointedness. I thought they're easier to construct. So that's actually extremely important. And this fails exactly because pi 0 is not a group. That's exactly what's going wrong in the proof. In fact, this theorem, and maybe I should mention it, is actually true much more generally. It's true whenever you have an infinity category, which is generated by a set of co-group objects. In this case, it will be our spheres Sn for n greater or equal than 1. But I decided for the purposes of this class to just present this special case. So the general case, it is sometimes useful. So it's not generality for generality's sake. Okay. So that's going to be the main theorem of this lecture. Before I prove it, I would like to deduce from it the promised classification of cohomology theories. Which is very easy, but also it has a slightly subtle point to deal with this connectedness that we are forced to put in this theorem. So as a corollary, let E upper star delta be a cohomology theory. Then there exists a unique collection of pointed spaces En and in Z, and homotopy equivalences En, I'm going to call them delta n, the loop of En plus 1, such that there are natural equivalences En of x, the same thing as homotopy classes of pointed maps from x to En, making the diagram commute. The following diagram commute. And let's see, we can have we have our D, which is an isomorphism here. And we have our isomorphisms with x En. And here we have maps from sigma x En plus 1. And remember, these, oh, pointed. Let me move this a bit on the right, actually. Remember, these by the loop suspension adjunction that I briefly mentioned last time is the same thing as homotopy classes of maps from x to omega of En plus 1. And here we have the delta n gives equivalence. So the map delta, this map delta here is induced by these delta n's. And again, let me actually mention that these delta n's are part of the data. You cannot like discard them and hope to have a useful thing. You cannot just ask them to exist, but without specifying them. These are the things that in the end you need to construct a boundary map in the long exact sequence of a pair. So they are important information.
Excuse me?
Yes?
You just said equivalences and natural equivalences.
Oh, natural, yeah, okay. Here I can say natural isomorphisms. If you want. These are in abelian groups, but I mean natural in X.
Okay, and the equivalences above, are these weak homotopy or just homotopy equivalences?
Well, I mean, En, when I say pointed space, sorry, I mean in this thing that's secretly n delta of Can star. So they're morally, I guess in classical terminology would say they are CW complexes. So there is no difference between the two notions.
Okay, thank you.
What do you mean by the uniqueness precisely? The standard uniqueness up to unique isomorphism?
No, I mean uniqueness up to isomorphism, but the isomorphism is not going to be unique. That's a subtle point I might discuss later. Concretely, these objects, En and delta n, are what we're going to call spectra. And the point is that the functor from spectra to cohomology theories is full but not faithful. So if you have an isomorphism downstairs, you can lift it up upstairs, but maybe not in a unique way. It's a slightly subtle point. It goes under the name of phantom maps. We might discuss them, or actually might put, maybe not this week, but next week as an exercise to constructing a phantom map and see exactly what happens. A phantom map is a map of spectra. Well, I haven't defined spectra. A map of this data that induces the zero map of of cohomology theories, but which is not null homotopic. So these things exist, as much as you might desire them not to. But such is life. Okay, let me get this corollary from the main theorem, unless there are other questions about the statement of the corollary. No, okay. This corollary also sometimes goes under the name of Brown representability theorem, by the way. So it's slightly less general than that. So, okay, one direction I am actually going to leave as an exercise. We did most of the information last semester actually, but that such data determines cohomology theory is left as an exercise. I might say a couple of words about where the abelian group structure is coming from, but for now, let me just do the other direction. From a cohomology theory, construct such data. Okay? So the first step is to prove for every n that En restricted to connected pointed spaces is representable. Using the Brown representability theorem. So we don't want it to be representable for every space, but let us first show that it satisfies the hypothesis of the Brown representability theorem. So, okay, what were these hypotheses? Where did I put them? Here. Okay, the first hypothesis is going to be obvious. So we have these sense wedges to products, and we have this exactness hypothesis. So let's go back here. The hypothesis one follows from the definition of a cohomology theory. And if you want, the fact that products in abelian groups are the same thing as products in sets. But okay. Okay, so the key point is hypothesis 2. And hypothesis 2, well, so we have a push-out diagram. And we want to show that En of E prime, En of Y, sorry, En of Y prime, En of Y, En of X, En of X prime is on 2. That's our goal. So the first remark, maybe I should have meant before, that the push-out diagram, push-out square, star, induces an equivalence between the mapping cones, the cofibers of F and the cofiber of F prime. That's again because so these we also see these last semester, but let me recall how the proof works. How did it work? Oh yeah, sorry. I should have come more prepared for this, but okay, doesn't matter. You consider this square here. I think that's right. Yeah, I think I did this right. Oh yeah, of course. Oh no, sorry. I'm doing it. I'm doing the pullback, not the push out statement. I'm sorry about that. And you take the co-limit of this diagram in the two directions. So if you take it first vertically and then horizontally, you get no. I'm sorry, I'm doing this wrong. Let me step on come for a minute. What do I want to say? Oh no, I'm sorry. This is a lot easier. Okay. Sorry. I was trying to prove a much stronger statement and I got confused. You just consider these two push-out squares here, and then you take the bigger square is also a push-out. So sorry about that. For 1 second, I got distracted and I was trying to prove a much stronger result, which we don't need. So if you got confused and you want to ask questions, that's the moment about this. That's the moment. Okay, so let me give a name to these guys. So that's, sorry, we call them x, y mod x and y prime mod x prime. Let me make this small in a corner because I don't want to have it here. So now we can write the two long exact sequences. We have en y prime mod x prime. This is going to be the long exact sequence for f prime. En of y prime, en of x prime, and en minus 1 or minus 1. I think it's going to be en plus 1 actually. I hope I'm not messing up the indices. It's not going to be important for the proof, but let me just hope I get this is en y over x. And we have a map of long exact sequences. And the point is that these vertical things here are isomorphisms. So in fact, you can get the subjectivity statement you're looking for from the snake lemma. but let me do it by hand, just to show you that this is not very magic. So this is, we want in this square here that the map from the bottom left corner to the pullback is surjective. So what do we have? We have alpha here and beta here, and these, sorry, this was f prime upper star and f upper star, and we have that. Oh, and then I should call them maybe this G and G prime. This is G upper star, G prime upper star. And we have that G upper star of alpha is F upper star of beta. That's the condition of, I give you a point of this pullback. And I want to find gamma, such that F prime upper star of gamma is alpha and G prime upper star of gamma is beta. So how do we do that? Well, the first observation, so here we have our delta. We have that wait. Oh yeah, the first observation, you can find delta of G upper star of alpha is the same thing as delta of F upper star of beta, which is 0. So going this way, you get 0. But going this way is the same thing as going this way. So, and since that map is an isomorphism, I'm telling you the delta of alpha is 0. Okay, then you can find gamma tilde such that alpha is F prime upper star of gamma tilde. Okay. Very good. That's almost what we need. It's half of what we need. We also need the thing is going to be sent to beta. So what we can find, well, we can consider beta minus G prime upper star of gamma tilde. We want this to be 0. It's not going to be 0. Let me call them beta 0 in general, but we might be able to fix it. Because if you take F prime upper star of beta 0, that's F prime, F upper star of beta 0, it's F upper star of beta minus F upper star of G prime upper star of gamma tilde, which is alpha minus G upper star F prime upper star of gamma tilde, G upper star of alpha, which is 0. As it should be. And then, okay, then beta 0 is, so we have beta 0 is delta, oh, and actually let me call them delta prime. Just to make sure, delta 0 is delta of some, what am I going to call this? Epsilon. But epsilon, remember you can lift it upstairs, since that is also an isomorphism. And so you can take gamma is gamma tilde plus delta prime epsilon, and this works. You can check it has all the properties that you want. This is just standard diagram chasing. You've probably seen it a billion times, but I like to be explicit from time to time. So, great. We can apply Brown representability. And so we can find Zn tilde, and you'll see 1 second why I'm calling them Zn tilde, such that for every x pointed connected space En of x is Zn. Okay, that's great. That's almost where we want to be, except that we would like this to be true for all x. But okay, now we can use the following observation. If x is any pointed space, then sigma x is connected. That, well, the point is that even if you have 2 connected components in the suspension, you're going to get this. And I'm pretty sure we mentioned it last semester because I make sure of it because I knew that I was going to need it. But if you don't remember it, I suggest you can see it, for example, as a consequence of Blaker's Messi. Although that's way overkill for this simple statement. Or you can just draw the picture and see that indeed it works. Every point has a path to the base point because it's a suspension and we are putting it by hand. So we have En of x is isomorphic naturally by delta to En plus 1 of sigma of x, which is isomorphic, sorry, this was tilde, to pointed classes of map from Ex to Zn tilde. But now we can use the loop suspension adjunction, and this is isomorphic to pointed classes of map omega Zn. And now, well, now we are done. Now we can just let En, the space En, to be omega Zn tilde. So remember, our Zn tilde actually were built so that they were always connected, because they were built in the category of connected spaces. But the representing space in general, of course, won't be. But that's not a problem, because the loop space of a connected space can be whatever, as we will see. Okay, not whatever, but as we will see, it can definitely not be not connected. Particular, okay, I could give an example with ordinary cohomology. And now we have, as before, En plus 1 sigma x is going to be maps from x to omega En plus 1. And so by the natural isomorphism, En plus 1 sigma comes from delta, sorry, you call it delta n by Ionida. And this ends up the proof of the corollary. Okay, other questions? No. So we have still roughly half an hour. Not sure if I can do the proof of the Urban representability theorem in half an hour without, I mean, I can, but I'm not sure if it could be a good idea. So let's see. I might defer the proof to next time and instead draw some more definitions out of this, if you think it would be better, if you agree with it. But first, do you have any questions?
Yes, you wanted to say something about getting the abelian group structure when you.
All right. Since I have time, I might as well say that. So let me give you a definition first, and then I'll say how you get the group structure. The definition: spectrum is the datum of a collection of spaces En for each integer n and equivalences delta n from En to the loop space or pointed spaces. Sorry, that's very important and I was forgetting. So the representability theorem is essentially saying that every cohomology theory is associated to a spectrum. I'm going to call this, we're going to call this, sometimes we're going to call the spectrum E. And just to be clear, sometimes I'm just going to define En for n sufficiently big. En for, say, n greater or equal than some big N. And then let, I don't know, EI to be just what do I need? N minus I for every E less than N. Since everything is supposed to be equivalent to the loops of the next space, if I define only from some space further, it's not. I mean, it still determines the whole sequence. It actually matters only what happens for very big N. The smaller guys are sort of determined by that. Okay. So now let me tell you how you get a cohomology theory out of a spectrum. So from a spectrum, we want to get a cohomology theory. And as I said, this is not going to be quite a bijection. And in fact, we will see spectra are much better behaved objects of than cohomology theories. So we're actually going to work with spectra throughout this course. So what's the idea? Well, the idea is you define En of X, just pointed maps, pointed classes of maps. So if you want, I can write this as pi 0 of maps, of pointed maps, sorry, from X to En. And by point map star, I mean if you want map space star, mapping space in this infinity category space star that I defined. Okay, well, we certainly have a suspension isomorphism. by the loop suspension adjunction using delta n. But as you were noticing, this a priori is just a set. In fact, in the exercise sheet, there's going to be an exercise asking you to prove that in the definition of a cohomology theory, you can just put set. If you say it in exactly the right way, the abelian group structure is automatic. But rather than do the exercise for you here, I'm going to tell you how, from a spectrum, you automatically get something that's valued in abelian groups. And the trick is, well, I said En of x is pi 0 of maps, pointed maps, sorry, from x to En. But that's, for example, pi 0 of pointed maps from x to, I don't know, loop squares of x n plus 2. And now loops being a colimit, or just the definition of mapping spaces, you can move it out. And that's pi 2 of maps En plus 2. And this gives an abelian group structure to En of x. That's natural in N. And it, in fact, if you unwrap also the suspension isomorphism is going to be an isomorphism of abelian groups. If you unwrap what it means. That's because pi 2 is an abelian group by the Ekman-Hilton argument. And the exactness, okay, the axiom 1, the product axiom, is just the universal property of coproduct. No? And then axiom 2 is exactness for Puppe sequences for any t, x t, sorry, x double prime t, x t, x prime t is an exact sequence of pointed sets. Which, if I recall correctly, was an exercise last semester.
Could I have a question?
Sure.
So in the definition of abelian group, you could use higher pi I.
Yes.
And probably this gives the same answer, but something has to be checked, right?
Yeah, you can check, but that's essentially because how you define the suspension of isomorphism, everything commutes. Everything that has to commute commutes. I mean, it's the Ekman-Hilton argument. So the Ekman-Hilton argument that we saw last semester shows that pi n omega x equivalent pi n plus 1 of x is an isomorphism of groups for n greater or equal than 1. So you have two group structures on this group, and they are and the naturality of the group structure of Pn forces the two group structures to commute to each other, and then the Ekman-Hilton argument tells you that the two group structures then are the same, and in fact are abelian. And that's what you have to check. But that's on some level, this has nothing to do with cohomology theories. This is just a property of higher homotopy groups and loop spaces. Because right, the group operation here, if you remember, is given by composition horizontally, and here, sorry, vertically, and this is somehow given by composition horizontally, but you can rotate them around, so to speak.
Okay, thank you.
Okay, so this is how you go from spectra to cohomology theories and vice versa. And actually, since we're here at this point, I'm going to give definition infinity category of spectra is just limit of omega of this tower. So concretely, objects are sequences En delta n. Sorry, I got En plus 1. And here actually I'm specifying them only for n greater or equal than 0, but for what I discussed, that's not a real limitation, since you can always extend it in a canonical way to all integers. And maps, so map from E to F spectra is the limit map En Fn in pointed spaces, i.e. a map is Fn and for every n, and this is important, it's very important, we're talking about homotopy limits here, so we give a homotopy here. Homotopy that I don't know, let me call it Hn. And this homotopy is part of the data of the map of spectra. And you can actually see that if you do a map of cohomology theories, you are still giving these Fn's, but then you're just asking that this square commutes up to homotopy, and you're not giving the homotopy. That's exactly why the map from spectra to cohomology theories is not full, because we are forgetting data, and this data is important. And I really hope that by the end of this class, every time someone writes a commutative diagram and doesn't, you feel uncomfortable if they discard the coherences, because they're really, really important. And you do get big problems if you don't remember them. Okay. So this was essentially to define also what a map of spectra is. But since we're at it, I defined the whole infinity category because why not? And sorry, this maybe I should have said what the map here was, but the map is just taking the loops of the maps. And landing, okay, this is technically a map from map omega En plus 1 to omega Fn plus 1, but you can use delta to identify them. So such an identification is exactly the datum of such a diagram.
Are all inverse limits in cut infinity computed on the level of simplicial sets?
Co-filtered ones.
All co-filtered, yeah. Okay.
No, but actually, no. You're actually, I'm actually slightly cheating because a point in this limit is not just a limit in simplicial sets, because you need also these maps to be fibrations, which they are not.
Yeah.
So what I'm saying, a point in this limit is a point in each of these stages plus a path from the image of the point to the next one. And this square is exactly such a path. Oh, sorry, or if you want this delta is such a path. And when I say path, I actually mean equivalence, sorry. Under the identification of Kant complexes. And
okay, so having these deltas makes up for the fact that their omegas are no vibrations. So.
Exactly.
Okay, thanks.
This is similar to how you define the homotopy fiber, which is also an example of a homotopy limit. Are there questions about this?
Are we going to use the higher simplices of this infinity category, or are we just content with objects and maps?
I mean, we are going to use at the very least homotopies, which you don't need to I mean, if you're uncomfortable because you're afraid of not being able to define these things, let me write what a homotopy of these things is for you, just for these ones. So a homotopy between two of these things is going to be a collection of homotopies I'm going to call Kn from Fn to Fn prime. And then, well, okay, let me write it like this. And then you have to extend no, sorry. And you have Hn tilde such that Hn, so this is Kn, this is omega Kn plus 1, and this is Hn tilde extending Hn, in the sense that when you, and the Hn prime, in the sense that when you restrict it to En times 0 and En times 1, this gives you the two homotopies. I could make a formal proof of this, but I don't know if it's worth it. It's essentially a path in the limit is a path at every point here, plus a homotopy of paths for every map in the diagram. But okay, I'm never going to use this explicit formula. That's never going to happen. I'm going to use, so that I'm going to be able to compute homotopy limits and homotopical limits in spectra. So I'm using the existence of these higher simplices implicitly, but I'm not going to use what shape they have. Does this make sense? And I'm always going to use tricks to reduce to the computation of homotopy limits and colimits in spaces. That's in fact a big part of what next lecture is going to be about, to show how you can use those tricks to never having to think of complicated diagrams. Just the complicated diagrams exist, you're happy that they exist, but you try to touch them as little as possible. I don't know if that was a satisfactory answer. And I mean, actually, why can't I give you the higher simplexes? So let me give an n simplex in map spectra E to F. It's just, let me say, an F from E times, sorry, E, oof, no, an M simplex, sorry, I have too many M, to Fn, and Oh, sorry, this was actually silly. I want homotopias relative to the base point, so I have to do this. Okay, is this concrete answer? Because an M simplex here spectra EF is an M simplex in map pointed spaces EMFN plus, and actually I don't know why I put the geometric realization since I told you I was working with, oh, because I didn't want to define what the loop of a non-Kan complex is. I see. Plus a path like this, plus a path simplex sigma n between omega sigma and n plus 1 and sigma n in map delta n space n. Okay. That's just how you compute the homotopy limit. Actually, probably should have given this formula for the homotopy limit of a tower last week, but we were already doing plenty of technical things. Is this a sufficient answer? Yeah. Okay.
Yeah. You just talked about the explicit formula for like sequential colimits. You could just put it in the script and we can read it there, or just give a reference.
Yeah. I'm going to put it in the notes. Sorry, I'm terribly behind in writing the notes, but okay. Let me actually write it in this. This is going to appear. And let me just write it, this formula. I'll actually have to think about a reference because this is one of those things that everyone knows, but no one writes. But limited point and then simplex in lim nxn is is collection n and gamma n's paths from, so if you have a tower, say fm, okay, pm plus 1, etc. This one in home delta m x action. Yeah, let me write it down. Actually, let me write it down. If we have a tower of spaces, then an M simplex and the homotopy limit is such a thing. And I mean, I could put a reference, but I'm not sure. Well, okay. I'll try to find a reference that spells it out. It is a consequence of a bunch of standard facts that I didn't want to explain. But it's a consequence of the fact that the tower is a free category on a graph. and that limits on free categories over graphs are simpler to describe. I'll try to find a reference that that spells this out explicitly.
Okay, thank you.
Other questions? If there are no other questions, I think I'll stop the recording, and next week we will prove the Brown representability theorem and do some stuff about spectra. If sounds good. Okay, let me stop the recording.